All right, let's jump right into this. Welcome to The Explainer. Today, we are unpacking what might actually be the greatest cosmic detective story in human history, the thrilling scientific hunt for extraterrestrial life. For decades, humanity has been scanning the stars, waiting for some kind of definitive signal. But what if the strongest clue we've ever found isn't a massive radio broadcast, but a microscopic chemical footprint floating in the clouds of a distant exoplanet? Well, today we're going to explore the incredibly fascinating evidence coming from a world known as K-18b.
Okay, look at this number, 99.7%. Now, this isn't just some random statistic we pulled out of thin air. This actually represents the current scientific probability accuracy level for a monumental discovery made in the atmosphere of K2-18b. It is an incredibly strong indication that the data points towards something biological, potentially even alien life. But, as you probably guessed, in science, getting from 99.7% to an absolute, undisputed fact is a massive journey. So let's take a look at the crime scene where this data was gathered.
The prime suspect in our investigation is exoplanet K2-18b, and it's located a mind-boggling 124 light-years away from Earth. This whole investigation into this distant world is being spearheaded by Dr. Niku Madhusudan and his team over at Cambridge University. But this sets up a huge mystery for us right out of the gate. How on earth do we investigate a location that is literally trillions of miles away? The answer lies in some of the most ingenious engineering humanity has ever achieved.
So it all started back in 2009 when NASA launched the Kepler Space Telescope. It was designed to stare out into the dark universe and look for stars dimming, which is a telltale sign that a planet is passing in front of them. But in 2013, disaster struck. Two of the telescope's four reaction wheels, which are basically its steering wheels, completely failed. It really seemed like the mission was over. However, NASA engineers came up with this brilliant fix. They used the actual pressure of solar radiation, kind of like a water raft riding the current of a river, to stabilize the telescope. They renamed this reborn mission K2, and because of that incredible save, in 2015, the telescope discovered our target, K2-18b.
Now, the physical dimensions of K2-18b tell a really incredible story. It's classified as a mini Neptune. It has 2.6 times the radius of Earth and 8.6 times the mass. Now, you might be wondering, why does this matter? Well, that specific mass-to-radius ratio perfectly proves K2-18b isn't just some giant ball of rock. If it were pure rock, its mass would actually be around 17.6 times that of Earth. But it's also not entirely gas, like Jupiter. Because the mass is lower than a rocky planet of that size would be, scientists realized it must be made of something else, and that something else points directly to a massive global ocean of water.
But here is where we hit a bit of a wall, and I want to pose this crucial question to you. Based on K2-18b's distance from its red dwarf star, its predicted temperature should be around -8 degrees Celsius. At that temperature, a global ocean wouldn't be liquid. It would just be a solid block of ice, right? So how could liquid water possibly exist there? Well, scientists hypothesize that the planet must have a really thick atmosphere acting as a giant greenhouse shield, trapping the star's heat and keeping those oceans from freezing over. But to prove this, we needed to know exactly what that atmosphere was made of.
To figure out the atmosphere, scientists use a truly brilliant method called transmissions spectroscopy. Here's how it works. When a planet passes in front of its star, the star's light shines right through the planet's atmosphere. Different gases in that atmosphere act like a filter, blocking very specific wavelengths of light. By looking at the light that finally reaches our telescopes, scientists can see exactly which wavelengths are missing. Those missing pieces act as perfect chemical fingerprints of the planet's atmosphere.
It turns out, different elements absorb specific nanometer wavelengths. For instance, sodium blocks light at 589 nanometers, hydrogen blocks at 121.6. In 2018, using the Hubble Space Telescope, scientists detected blocked light at precisely 1400 nanometers. This was a massive breakthrough, guys, because it absolutely confirmed the presence of water vapor in K2-18b's atmosphere.
But, you see, Hubble had its limitations. Its infrared vision is limited to a really narrow band between 1100 and 1700 nanometers. Within that range, the fingerprint for water vapor and methane look remarkably similar. It's kind of like trying to watch a complex movie on an old black and white TV. To get the full picture, humanity needed a serious upgrade. Enter the $10 billion James Webb Space Telescope, or JWST. This telescope can see from 600 all the way to 28,000 nanometers. It's literally the equivalent of a 4K HD color TV. Plus, it operates at a freezing minus 233 degrees Celsius, which eliminates electromagnetic noise and gives us incredibly pristine, high-resolution data.
Armed with this new technology, Dr. Madhusudhan's team proposed a really fascinating concept. K2-18b might be a Hycean world. That name actually comes from combining hydrogen and ocean. A Hycean world is defined by incredibly deep oceans covered by a thick atmosphere that is 10 to 90% hydrogen. This hydrogen acts as a powerful greenhouse gas, keeping the whole planet warm. Now, if the ocean is too deep, extreme pressure at the bottom could create an impenetrable barrier called Ice V7, preventing vital minerals from the planet's core from reaching the water. But if the conditions are just right, this hydrogen shield could perfectly incubate life.
But wait, can life actually start in a massive ocean under a hydrogen sky? To answer that, we have to look back at the famous 1952 Miller-Urey experiment. Scientists basically combined hydrogen, water, and methane, which, by the way, are the exact raw ingredients predicted on a Hycean world, and they applied electrical energy to simulate lightning strikes. The result? They actually sparked the creation of 20 different amino acids. This brilliantly proves that the fundamental building blocks of life can absolutely be forged in these exact chemical conditions.
So fast forward to September 2023, and the James Webb Space Telescope finally turned its giant golden mirrors toward K2-18b. The results were monumental. JWST definitively confirmed the presence of methane and carbon dioxide in the atmosphere, which perfectly aligns with the Hycean World model. But then, it dramatically revealed the most explosive clue of all, the detection of a molecule called dimethyl sulfide, or DMS.
Okay, the absolutely crucial point here is understanding what DMS actually is. On Earth, dimethyl sulfide is a molecule produced almost entirely by biological marine life, specifically phytoplankton and algae. It is quite literally what gives the ocean its distinct smell of the sea. Aside from life, there are almost no natural processes on our planet that create DMS in significant amounts. And yet, JWST found chemical fingerprints suggesting DMS on K2-18b in quantities 1,000 times greater than what we have here on Earth.
I know, this sounds like the ultimate biological fingerprint, right? But I really want to ask you this. Is the discovery of DMS absolute, undeniable proof of alien life? As enthusiastic as we all are about this, and trust me, it's exciting, we have to pull back a bit and lean into the rigorous, impartial scientific skepticism required for a claim this massive. Let's look at how the scientific community is actively debating this data.
Remember that 99.7% number from the very beginning of our explainer? Well, that represents what scientists call a 3 sigma level of accuracy. It is a very strong indication that the data is correct. But in astrophysics, the gold standard for claiming an absolute world-changing scientific discovery is 5 sigma. That requires 99.9999% accuracy. Right now, Dr. Madhusudhan's data sits at 3 sigma, meaning there's still a tiny, roughly 0.3% fraction of doubt that prevents it from being a confirmed 5 sigma discovery.
So, what are the actual roadblocks here? Well, non-biological sources of DMS could theoretically exist. In laboratory tests, scientists have successfully created DMS without any life at all, simply by bombarding a mix of hydrogen sulfide, methane, and CO2 with UV light. Furthermore, trace amounts of DMS have actually been detected on comets right here in our own solar system. For this to be absolute proof of life, the scientific community must definitively rule out any unknown, non-biological chemical reactions that could be occurring on K2-18b.
And then, honestly, there is the biggest mystery in the entire dataset. Where is the missing ethane? According to our current chemical transmission models, if biological DMS is present in the atmosphere, another gas called ethane should be produced as a natural byproduct. It should be highly visible in the JWST scans, yet it is completely missing. This missing ethane is really splitting the scientific community right now. Are our transmission models incomplete, or are we somehow misinterpreting the light signatures?
To solve this puzzle, the team has a pretty intense to-do list. First, they have to wait for more JWST observation time. And let me tell you, telescope time is highly competitive. Once they get it, they need to gather enough data to finally achieve that 5 sigma certainty. They have to locate the missing ethane, confirm the expected lack of ammonia, and perfectly distinguish the DMS signal from other similar chemical structures. Massive discoveries just require immense patience and really rigorous peer review.
We are literally standing on the very edge of history right now. The investigation into K2-18b shows us just how incredibly precise our tools have become. Whether it turns out to be a global ocean teeming with alien phytoplankton or an entirely new geological process we've never seen before, science is inching closer than ever to answering humanity's oldest question. Are we alone in the dark universe, or is advanced life already looking back at us? Thank you so much for joining me on this explainer. Stay curious and keep looking up.